Good afternoon, everyone, and thank you for joining us today. I'm Desi from Clean Air Partnership, and today with me on the calls are our guest speakers, which is Kelsey Sanders and Rian Devraj Kizuk. They will introduce themselves shortly. Our webinar today is on new design resources for embodied carbon targets. I wanted to start first with land acknowledgement. Clean Air Partnership is Toronto-based organization, and we acknowledge that the land on which we operate is the traditional territories of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis people. In the next 1 minute, I just wanted to share a short video with you so we can learn something from Indigenous peoples about Indigenous peoples.
Us as Anishinaabe people, we believe that our hair is seen as like an extension of our spirit. So we believe what makes us human beings is we have four parts. You know, we have our mind, we have our body, we have our spirit, and we have our heart. And so we almost view our hair on our head like an extension of that spiritual part of us, as opposed to just being something that grows off of our body. And the reason that we braid it into these three strands is because we believe that when we braid our hair and braid our spirit into those three strands, it's actually honoring and representing very important parts of ourselves. So things like our mind, our body, and our spirit. Those three strands that we braid together are also recognized and seen as being our past, our present, and our future. These three strands also represent those before us, ourselves, and those after us. So those previous generations, ourselves, and those future generations. So for us.
Thank you for watching this. I learned something new. I hope you too as well. I'm going to bring you back now to some of our resources. We have the climate policy database, which track the climate-related policies across CAC network. Now it's easier to see and access those policies. And then with the Climate Action Atlas, we track implemented ambitious mitigation projects beyond CAC, because we feature some very good leading examples from other municipalities across Canada. I'm going to share a link to those tools shortly in the chat. And lastly, I just wanted to show to you what is coming up on November 30th, which is this Thursday. We are going to have City of Calgary presenting to us more on their adaptation and resilience implementation. This is part of our ongoing climate governance, accountability, and implementation series. And on December 13, we are going to talk about barriers to implementation, what prevents municipalities from building more complete streets and Vision Zero infrastructure. I'm going to share a link to our events webpage where you can access and register if you're interested, but also if you want to be in tune of what's happening in upcoming events, you can subscribe to our newsletter, and I'll share a link to that as well shortly. But without further ado, I want to give the words to our presenters, Kelsey and Rian. They will introduce themselves as well. Please take it away.
Thank you. Okay, Rahana, if you want to share.
Meanwhile, I wanted to let know to our audience, as usual, use the chat or the Q&A box for your questions. We'll have time at the end of the presentation if you want to ask your questions verbally. So that's the house rules here. So take it away, Kelsey and Rian.
Okay, I think I have control. Okay, for some reason our cover slide isn't showing, but that's okay. We'll start off with today's agenda. So as Desi mentioned, we're presenting here on new design resources for embodied carbon targets. And the context here is within the built environment, and particularly the building enclosure of our buildings. So we're going to start off with a whole building life cycle, just a bit of a high level overview to set the stage about what we're going to be talking about and why this research we felt was necessary. The relationship that we have with Toronto Metropolitan University and how that grew into this 2023 recently launched embodied carbon study. Rahana is going to then take over and discuss the project in more detail, go through an overview, run through our methodology, as well as the results of the study. And then I'm going to take it back to talk about some key takeaways and next steps. So just a brief introduction for both of us. So I'm a senior building science consultant with RDH in our Toronto office. We are a North American company, so we have offices kind of across the US and Canada with just 300 employees. It's fairly small. And what I do as a building science consultant is primarily new construction building enclosure design. So that's supporting design teams in developing their building enclosure systems and then making recommendations for specific products. Whether it is about durability, water, air, heat, thermal transfer, so thermal performance, as well as the overall life cycle carbon emissions, so the materiality of those enclosures and how much they contribute to whole life carbon emissions. My background is in architecture, and then I did a master's in building science, which has brought me to this field. Rahana, do you want to take over?
Yeah, hi, thanks for having us today. My name is Rahana, and I'm a Passive House project manager at RDH. And in my role, I work primarily in high performance projects on integrated service projects. So while I work on the energy side of these projects, managing as well as conducting energy models and sustainability analyses, we also include enclosure work as a deep and integrated part of those projects. So I work with Passive House as well as zero carbon building projects and Toronto Green Standard and other high performance sustainability structures like that. My background is in civil engineering with a building science and environmental specialty. And I worked in restoration for a number of years before moving over to the energy sector.
Great, thanks, Rahana. Okay. Sorry, just seeing a bit of a lag. So I feel like we're in a savvy audience here, very familiar with climate change and the risks associated with that. It's no secret that we're in a climate crisis. So we're seeing higher frequency of extreme weather events, and these are causing devastation around the globe. So how do we act as an industry? Obviously, for us, the buildings industry contributes nearly 40% of all GHG emissions. So we really need to be not only acting immediately to address these, but also thinking about the future of our buildings and the built environment. So what are the two kind of levers that we have? So there's two primary, which are climate change mitigation. So that's like reducing the overall impact immediately of our buildings. And so we can do that through the reduction of operational carbon emissions, which has been the primary focus for the last, let's say 10 years, 20 years even. And then secondary, to reduce the embodied carbon emissions of the materials that we're putting into the construction of our buildings. And that is something that we're talking about today, and it's becoming a more, much more at the forefront of our focus in terms of our consulting work and in terms of the building industry as a whole. The second is climate change adaptation. So the consideration for what we expect to see in the future. In the design of our buildings now, we need to be considering future environmental loads and consider those extreme events, such as extreme drought, flooding, and extremes in temperature, as well as things that we're seeing heavily today, such as the extreme increase in incidence of forest fires, as one example. Sorry, it's not progressing. There we go. Okay. So as I mentioned, the buildings and the construction industry represent about, let's say 37%, about 40% of global operational emissions. and process-related CO2 emissions. So this is, in case you're not familiar, this is essentially the life cycle emissions of a building. It comes from the embodied, so what we call embodied emissions. It would be like the process loads that go into a material. So that's the raw extract, the energy required to extract that raw material, to transport it to the factory to be manufactured into the material that we're going to use on site. It then needs to be transported to the site. It needs to be, the building is being constructed. There's energy and process loads required for that. The use and maintenance of the building. So that would be our operating energy, but also in replacing the materials over time, depending on their expected service life. So you might replace your glazing every 25 years. You have to account for the embodied emissions of all of those front end processes required for that glazing system to come to this existing building and be replaced. And then there's the demolition of the building, hauling away the materials, and the materials going to landfill, and ideally being recycled as part of the kind of cradle to gate approach. Or that circular economy. So what can we do? There's two primary things we need to start off with. First, we need to understand the true and complete impact of buildings. So far, as an industry, we've really been focusing on only a small piece of what the true impact of our buildings are. So we need to really understand the full picture. The second is, as previously mentioned, to mitigate and adapt as an industry. In terms of buildings, I'm going to talk about, there's kind of these three different approaches, each related to that mitigation and adaptation. So for mitigation, we have reducing the operating emissions and then using low or zero carbon fuel sources to fuel the energy requirements of that building. So in this graph, we're looking at this is an example of a long-term care facility. It has an 80-year service life. So we're looking kind of from today, 2023 to 2100. And the building's built to code minimum, which means it has a higher operating energy or operational carbon. We can kind of equate those two things relatively. If we're talking about like fossil fuels, for example. And then the carbon emissions at construction, that's our embodied energy, that's that orange bar. And the embodied emissions are generally, they're all up front, and then you see a little bit of orange as the life of the building progresses and at the end of its life. And during the service life of the building, that just means your maintenance, replacement of parts. So in this pie chart, if we have a pie chart here on the right, like let's say about 80% currently of say a code built building would be operational carbon, and only 20% would be embodied carbon over this 80-year service life. But if we, rather than using building code minimum as our target, if we have a high performance building, we're going to drive those operating loads down. So the operational emissions are going to be reduced. And then we can also move to zero fossil fuel sources. So that in Ontario, that can mean electrification because we have a very clean electrical grid. So that would be reducing further our in carbon emissions related to operations, also using renewable fuel sources. So you can see that overall the loads, this pie chart has gotten smaller, but also the mix, the ratio of embodied to operational has changed. We have a much higher contribution of embodied than we did previously. So it's about a 50-50 split. Finally, we can reduce the emissions associated with building materials. So this is using fewer materials, using materials with lower GHG intensity, and making the materials last as long as possible. So that's early on in design, understanding what materials am I using, what materials am I specifying, and ensuring that those are all low carbon, using less of them, and then durability. So designing the building for durability, and that comes in with detailing. So if I've optimized for low operating carbon here, in reality, if we're talking about our targets to 2030 or to 2050, we have a very small window, a couple of decades, to significantly impact future climate change. And this is based on research by the IPCC. So if we now look at only this next kind of 30 years, embodied carbon becomes 80% of the pie. much more significant than our operational carbon. We know that a lot of our buildings are becoming a lot more energy efficient because codes and standards are changing. So we really, really need to focus on this embodied carbon piece. And then in terms of this front end piece, so this is the embodied carbon in our materials, we have construction activities, transportation of site, and production of materials. In the study that we've done with TMU, we've only focused on the production of the material. So we're not talking about anything past the material being manufactured in the factory. We're not getting it to site and in construction yet, but that's the biggest piece of the pie overall anyways. We're focusing on this aspect just because we don't actually have a project site. So we're keeping it generic for the purposes of this study. In the study, we're looking at walls, roofs, and floors, not looking at anything structural at this point. Just a quick nod to durability in buildings. So you can design a building to be as low carbon and as energy efficient as you want, but if the materials aren't durable and made to last, and if the building isn't detailed well, let's say call it airtight, and detailed to be water shedding in a way that's going to make the materials last as long as possible, then it's kind of a moot point because there's going to be so much need for maintenance and repair and replacement over time. So durability is a really key component of the whole picture of a building's full life cycle carbon emissions. There are new standards and codes coming into effect in Canada. This is looking at the full Canadian landscape. So we have the Canadian Green Building Council Zero Carbon Building Standard. This is in place, although it is voluntary, but it does now have a set requirement in the newest version for maximum whole building carbon emissions per square meter, which is 500 at the moment. The Toronto Green Standard version 5 is coming soon, 2025, but even in the version 4, there is in tier 2 and above, there is a set target for embodied carbon, which again is 500 kilogram per square meter per year. And then there's the National Building Code and NECB. Embodied carbon is also coming to those in 2030. And then the proposed ASHRAE standard 2040P is also coming soon. This is going to be to hopefully level the playing field in terms of how LCAs are done so that you can compare one to another. The City of Toronto targets all existing buildings retrofitted to net zero by 2050 as well. So this is going to substantially help. Obviously existing buildings, rather than demolition, retrofitting them is going to be your lowest carbon approach to a new building. So with RDH and TMU, I went to TMU in my undergrad, and so did my colleague Erica. So this really stemmed out of her and I had been getting questions from clients all the time about, how do I build a better building by reducing my embodied carbon emissions, asking us questions about specific materials. And we just felt like we didn't have enough resources internally and externally to look at to provide the best consulting advice that we could to help them to get there. And so we had a couple of internal working sessions, and then we decided to try and partner with the university to get some funding to really dive deep into this. And that's where this study came to be. So we approached TMU in 2021 and kicked off with TAF funding in early 2022. It felt really well with already approved ongoing studies at TAF. So the City of Toronto was doing a study with the University of Toronto and Mantle Developments to do a benchmarking of all of the a lot of buildings and LCAs currently completed to see what should they be setting as a reasonable target for embodied carbon emissions for a building in Toronto. And then also one very similarly, but for single family residential or small scale residential by Chris Magwood. Our use case was initially intended more on the lens of designers, but really it started to broaden for manufacturers and policymakers as well. So the use case is to be a tool for early design stage life cycle assessment and decision making, and to inform decisions at both a project but also at a policy level. The final guidance document and website are now live. I put a link here for when we share the slide deck, but Rahana is also going to run through that with you now. So this research was a response to a call for action. We're talking about carbon now. This is what's important. It is the new what was energy. So we used to talk about energy a lot. Energy and carbon are equated, just depends on fuel source and kind of where that energy is coming from. But carbon is the real metric we need to be concerned about. Decisions made early in design have a major impact on the whole life cycle carbon of a building. So I mean, we've all probably seen this graph used in some way or another, that the ability to influence the success of a project or a decision is very high at the beginning and very low cost. Whereas as you start to get later on in the project, say when you do an LCA at the very end of a project, which has been typical, the cost of implementing a change to try and make an improvement is significant, and the ability to do so is very, very low. Current standards are addressing this issue as kind of an end of the stage project, an end of project stage, so like past construction report card service. And that's not really doing anybody any service because you don't have any opportunity to make any improvements prior to the construction of the building. So the industry needs accessible, let's read kind of simple resources that support early stage decisions to reduce upfront carbon. And the industry needs more benchmark data to inform policies in addressing the whole life cycle carbon balance point. So what is that? It's essentially the balance between operational energy reductions and embodied carbon emissions. Obviously, when we're trying to reduce energy as much as possible, what happens is we tend to be adding materials to buildings to reduce their energy. And every single one of those materials has an embodied carbon impact. And so where is the balance point of trying to make buildings as energy efficient as possible to reduce operating emissions, but also not just throwing materials at it so that we're significantly increasing this initial upfront cost of carbon. Now I'll pass it over to Rahana.
Thanks, Kelsey. Yeah, so I'll take it from here. What I'm going to get into is sort of the technical meat and potatoes of what our study aimed to accomplish, its usability, some of the research methodology that we used, and then I'll showcase the results. So first of all, a project overview. So responding to that call for action that Kelsey was describing, to recognize carbon as the new energy and to meet ever-changing industry demands and needs for better understanding of embodied carbon, we defined these 3 objectives for our research project at the beginning. So the first is to develop a standard methodology to calculate embodied carbon for enclosure assemblies. The second is to utilize that methodology to calculate metrics for 26 different building envelope systems. And the systems we chose are commonly used for new construction within the Greater Toronto and Hamilton region, predominantly Part 3 buildings. And we did include a few retrofit assemblies as well because they are quite important, and we want to draw attention to the fact that that all buildings need to be retrofitted at some point to reach our industry target goals. And the third is to develop design support guidance for multiple use cases that will allow expertise and knowledge to be shared with design teams so that we can make informed decisions when considering low carbon building envelopes. So in order to meet those objectives, the following outcomes and deliverables are prepared. First, we have a full database for public access that includes all of our calculations, all of our assumptions that designers can download and use for their own building typologies in their own regions, as well as for multiple other use cases that I'll get into in the next couple slides. We've released cut sheets for each and every assembly where we performed calculations, and they show total embodied carbon emissions as well as the emissions for each individual material layer within the assembly. And then our guidance document, you can find even more specific comparisons between different options for each layer. We look into a sensitivity analysis for different cladding types and different insulation types, and all of that's available in our guidance document. And then lastly, we've included some guidance on who we think will benefit from this tool and how they can use it. And that's kind of what I want to go into now. So our first use case is for early stage design. As Kelsey mentioned, there are many embodied carbon targets that are being reflected within codes and standards in the industry. And if we have those targets, then within the early stages of design, we can plan to hit those targets. So at the beginning of design processes in concept and schematic design, we don't often have details of our enclosure assemblies, and that makes the processes that are required for LCA analysis, evaluation of quantities of materials, knowing what material areas for our EPD selections will be challenging. And it's not feasible at that stage of the project to develop detailed drawings for multiple different enclosure assemblies. So one of our hopes is with this tool, we can provide material descriptions and material quantities for all of the assemblies that we've selected, and that data can be used as a starting point to understand which materials are dominant for whole building carbon emissions, and designers can seek improvement by modifying that data and substituting project-specific information to suit their own contexts. Secondly, for codes and standards, we spoke about this a bit earlier, but the codes and standards that set targets for embodied carbon emissions often use a benchmarking process that relies on previous building experiences. So we know what the past decade or 2 decades of building carbon emissions are generally produced. So as the industry improves by reducing these embodied carbon emissions in the products and materials that we use, then we become more knowledgeable, we become more proactive, and as a result, codes and standards reflect that knowledge growth and update their targets to reflect new industry performance as it develops. But this process takes time, and it requires previous building experience in order to be able to update with targets that reflect the industry at its current state. So one of the things that we're hoping with this guide is that it can kind of short circuit this process. We can reveal the impact of enclosure selection on whole building embodied carbon before waiting for the next generation of buildings to be constructed, so that our targets and codes can evolve faster. Hopefully understanding that balance point between operational and embodied carbon emissions can support in further reducing these targets or transforming the targets into a whole life cycle carbon emission metric. So instead of considering operational and embodied carbon separately, we could combine the two and consider that as one metric as we move forward. Our next, two actually, points are for manufacturers. So our first bullet there allows our manufacturers to develop an understanding of the context of their projects or their products. So where their products fit within assemblies, which assemblies it's being used in, and how the embodied carbon emissions of their products contributes to that whole assembly amount. And hopefully understanding where their product fits in the global context, they can use that as a way to innovate and develop more options. Secondly, we want to encourage EPD generation. So availability of EPDs is a large limitation when conducting life cycle analyses. So we think that this tool will allow designers to focus their attentions on materials that have lower embodied carbon potentials, and then they can have the highest environmental impact with their projects and seek out alternatives. So the request for these alternatives can then incentivize manufacturers to develop EPDs for their own projects and move the industry forward. I'll jump into our methodology now. So something we like to say at RDH is that we have an enclosure first mentality. And this is where this study begins. So in operational carbon reduction, focusing on enclosure first means improving our thermal performance and airtightness to reduce the load carried by our building's mechanical systems. So that same sort of mentality is required in embodied carbon reductions. As we increase thermal performance, we're increasing the number of materials inside our walls, we're adding insulation, we're adding clips and fasteners and other materials that increase our embodied carbon performance in a whole building sense. So from that perspective, optimization is necessary to reduce our total cycle carbon emissions. Optimization can be complicated. So we have many material options coming together in many combinations. There are so many different design goals and objectives that projects can have. So there's a high level of variation when considering enclosures. And this makes for a diverse selection of study options. So that was one of the reasons why we focused on the building enclosure within this study. So there's two sections to our methodology. One is our assembly selection methodology, which I'm going to go through now. And then the second is the methodology for conducting the life cycle assessment itself. So we'll start with the assemblies, and using that enclosure first mindset that I talked about. These are our 3 steps for our assembly selection. First of all, in order to establish reasonable performance targets that meet the current needs of designers as well as meet future performance requirements of our local energy codes, we came up with these performance targets for our walls, roofs, and floors. And I'll go into a bit more detail on what an R value is, just to make sure we're all on the same page. So first of all, showing the assembly. Here we go. So what we're looking at there in the blue is considered a nominal R value. So that's the thermal performance of the insulation layer on its own, completely separated from the rest of the assembly. These are what you would find on a material cut sheet for an insulation property. Our next level up from there is what we call an assembly R value. So that's the orange box that you can see on the screen. Now we're considering a slice of the assembly that includes that nominal R value of our insulation layer, plus the thermal resistance or the performance of our other layers in the assembly, but it's taken in a linear slice. So it doesn't necessarily include other unique elements that are around it. It's just considering the 2-dimensional performance of that layer. And what our study uses is an effective R value, or in this case, a clear wall R value. So now we're considering that assembly R value that I talked about previously, but we're also considering 2-dimensional effect of other repeat thermal bridges. And what I mean in that case are these clips or fasteners. So that's metal products or studs or unique elements that aren't continuous throughout our system, but they do affect the overall thermal performance if you're considering a larger area. Going back to our methodology. So understanding our R value targets is where we started. And then secondly, we were able to select our assemblies. And we focused on, as I said before, commonly used assemblies in the Greater Toronto and Hamilton region. And we prioritized having a variety of materials so we could see range across our study and diversity. And then we also made sure to include a few retrofit options. So what I mean by assembly, and this is just a little technical aside, what I mean by assembly is the stuff that's mentioned in the skin layer. So the very outer layer in that in the diagram you see on the screen is called the skin, and that's basically anything that keeps the elements out, keeps heat in and water out. So that includes our roof, siding, windows, exterior insulation, and so on and so forth. The next layer in is the structure that holds up our building. So that would be columns, beams, rafters, joists. We don't consider those elements, but if there's a structural element like a concrete backup wall, you'll see in some of our assemblies, we do consider that because it is continuous across our assembly. And then anything internal to that is not considered. So with that information, we selected 26 different assemblies, and that includes all the materials that comprise a typical installation of that assembly. So that'll include our main control layers, as well as repeating thermal bridges. So that'll be cladding, fasteners, and attachments, insulation clips, or metal studs, concrete backup walls, that sort of thing. But it doesn't include linear thermal bridges, so that those are parapet transitions or transitions between subfloor and ground floor, or shelf angles, or major thermal bridges like that will not be included within the study. So here are our wall assemblies. As you can see, we've got a diversity of options here. So we have cladding elements such as brick. We have insulated metal and concrete panels. We have exterior insulated foam systems, and the retrofit assemblies you can see on the right side of the screen, W14 to 17, show the white layers of the assembly are what we are assuming would remain in place if this building was already constructed. For insulation, we have also a variety of insulations: material, wool, XPS, phenolic, spray foam, plenty of options to get a good range, as well as our backup materials. Here are 5 roof assemblies. And again, we tried to prioritize regionality as well as diversity. So we have built up roof, modified bitumen, metal roofing. These are all types of roofs that are very commonly seen in the greater Toronto and Hamilton region. Simple selection of floor assemblies, but we did include a suspended ceiling for a bit of diversity there. So next is that life cycle analysis, or the calculation of our embodied carbon metrics. And we start off here with our selection of tools. We used one-click LCA for our study for a number of reasons. It's an online software, and it has reporting alignment with over 40 different international certifications, many of which are commonly used in Ontario, as well as it has the ability to use specific environmental product declaration data, as well as global averages, and I'll explain what that means in a second. But other advantages are it has a great user interface, and the data uploaded to it is updated within 24 hours of receiving any new information. So that makes it a useful option. A note on tools. So at the top of the slide there, you can see a variety of different tools that are available for conducting life cycle analyses. There are many different types, and they all have different purposes. So it kind of just depends on where in your project you are, as well as what your project needs are. These different softwares can pull from 2 types of databases. The first database is an EPD database. So that will be a very product-specific piece of information. Usually manufacturers will produce this for a specific material in a specific region. The second type of database is a generic database, and those material data are based on industry averages. And we tried to use industry averages for the study as much as possible, so it could represent our Greater Toronto and Hamilton area to our best ability. And also represent the breadth of projects that you might see. within this region. So the next step in our LCA analysis is quantity takeoffs. In order to conduct a life cycle analysis, we need to have either volume or area takeoffs for all component parts within the assemblies. So we calculated those as was appropriate for whatever environmental emissions data we were using for that material type. And the functional unit that we used, so that's the area of the chunk of wall assembly or roof assembly that we are including within our system, was 9 meters squared, and that's relatively large. We chose that size so that we could account for all of our assembly components that might be missed in a smaller area. Yeah, this is just an understanding of LCA analyses. There are plenty of methodologies out there that present different ways to calculate embodied carbon emissions, depending on whether you have a single product or a system or a handful of systems, all the way up to a whole building analyses. But the fundamental principle of all of that is that we need the material quantity multiplied by a carbon factor, and that's what gets our embodied carbon emissions. So for our study, we have a 9 by 9 meters squared, and then here's an example of what you would see in our data sheet, where each of our material layers is described in detail, and the thicknesses and material volumes are calculated and shown there. The last step is to actually conduct our life cycle assessment. So our study focuses on stages A1 to A3. And again, I will explain what that is in a second. And we use the 60-year lifespan for our project. So our component EPDs were selected within the one-click database based on the most representative material that we could find available for that component's purpose and its material properties. And then the embodied carbon of the assemblies is presented in absolute values. A note on life cycle assessments, there are many different types of life cycle assessments. You can have a life cycle assessment for a single material all the way up to a whole building. So a building or material or component's life cycle is summarized in stages from its raw material extraction and product manufacturing through to its use, and then to the anticipated end of life. So it's demolition and it's material waste processing. So an LCA will provide an overall holistic overview of a project's environmental climate impacts. For our study, the output of the LCA that we were considering for embodied carbon emissions data falls under that global warming potential impact category. Here is a look at the boundaries of our scope. So in the brown dotted line, that shows kind of what a typical life cycle analysis could entail. So product stage, construction stage, use, and end of life are all outputs that you can generate through a life cycle analysis. But for our study, we focused on the study system you can see within the blue dotted line. So that's just the product and construction stage. We would need far more details and assumptions to include use and end of life. So we're focusing on the embodied emissions of the materials themselves. And now the results. This is a snapshot on what our website looks like. I'm actually just going to pull it up. So this is what the website looks like. We have a bit of background, and from here you can click to see our detailed guidance document. So we give a lot of background information on where in the industry our study has an impact, as well as we detail who we think can use this study and the implications of the data within. And then we dive into a lot of details on our methodology as well as we present our results. Here's an example of one of the cut sheets you can download for one of our assemblies. So this assembly is brick veneer with a concrete backup wall. The charts show the embodied carbon emissions for each material layer, but then we also have it summarized as a whole here below. And we've separated out the product stages A1 to A3, as well as shown A4 to C4, just to show the difference between those stages and the impact that the emissions produced by the materials itself has. You can see it's quite dominant in that overall embodied carbon emission calculation. And then we present how we calculated the R values for each assembly, as well as all of the data behind our embodied carbon emissions calculations. My math thing is actually hidden by the bar here. I'll go to the website. And if you on the website, if you click to on the headers, you can get a comparison of all of our wall assemblies together. So for example, you can see that here, W06 and W07 have a fairly high embodied carbon emissions calculation, and we can attribute that to the concrete within these precast assemblies. Whereas if you scroll down to our retrofits here at the bottom, W14 to 17, you can see that the embodied carbon emissions overall are much lower, and that's because those high contributing material layers, so the brick and the concrete, are assumed to be remaining in place. All right. And I'll hand this back to Kelsey to wrap up our key takeaways.
Oh, Kelsey, are you here?
Yes, I've been talking to myself apparently. Sorry about that, guys. So yeah, I was just saying that all of the data sheets, we're in the process of updating them, which is why Rahana was showing it the way that she was, but those will be live very soon, and you can download all of the cut sheets for each assembly right there on the website. Okay, so now into key takeaways. So some of the limitations and challenges of this study, of course, with any life cycle assessment, when we're dealing with EPDs, generic or project specific, it's challenging in the way that the data is gathered and the way the data is presented, and kind of our confidence with the data. So during the study, lack of a centralized lifecycle inventory just across the various platforms of the tools that are available. The use of generic EPDs that sometimes wasn't available to us for certain products. So we did actually have to go and use product specific EPDs, which may not be representative depending on the type of product that you are using. And then product specific information doesn't reflect, obviously it's not reflecting a regional average. And this goes into applicability of this overall, not just this is things we found during the study, but we anticipate being an issue across the board on LCAs, that EPDs represent the energy that went into manufacturing. So this is very regionally specific. So if you have a plant that's locally nearby and you think, okay, I'm going to use that product because it's going to have a lower impact on my emissions, the EPDs that you're using may not be for that factory. It may be an average for all of the manufacturing that occurs across North America, say for that product. So it's very regionally specific. The grid in Ontario is very clean, but this isn't the case everywhere. So if a product is manufactured elsewhere, they may actually have higher emissions because of their fuel source. And the energy used in manufacturing, if it's electricity, it's heavily just dependent upon their grid. Some of the key takeaways of the study and of this presentation. So the industry needs to rethink how we look at whole life cycle carbon impacts in buildings, balancing this upfront emissions and the life cycle operational impacts. That's finding the whole life carbon balance point. I think this is the key point to take away from this presentation. Considerations are most effective when included early in design. And this must be influenced by, of course, local policies and standards that are pushing the need to achieve lower carbon emissions and higher levels of performance in this aspect. Consider material durability and lifespan as part of this whole life cycle carbon review. So this includes the durability impact of architectural details and mitigating future emissions for replacement and repair. Using less material and selecting materials with lower GHG emission intensity is obviously going to have also a significant impact on this upfront carbon. And a simple form, so things that we already talked about as passive design strategies, simplification of form, a lower glazing ratio, and other important passive strategies, and they also tend to lend to lower life cycle emissions, both in operation, but also in embodied emissions. How do we envision this study being used? So obviously we want people to be able to reference the data in the study and adapt it to their own use case, which is why we think the volumes, the takeoffs and volumes are really valuable, because you can use the takeoffs and volumes and potentially use the global warming potential or the embodied carbon per square meter of that from EPDs, and just use the volumes that we're referencing in the study if you're using a different product, for example. Oh, I'm saying it right there, yeah. And then inform the schematic level estimates of enclosure related embodied emissions early in design. So we're already using, if you're not familiar with this tool that I'm showing on the right here, usually in schematic design, there's at least some form of massing or form. So we can understand, you know, what do we anticipate as a glazing ratio? And then what's the form of the building and what's the overall surface area of our walls, our roofs, and our floors. And we can take that information, and right now it's put into this spreadsheet for thermal performance, to enhance thermal performance and understand the implications of thermal bridging. This is from BC Hydro, Fortis BC PowerSmart, and it utilizes the building envelope thermal bridging guide to better understand overall building thermal performance, because we actually have targets for this, and these spreadsheets need to be submitted, at least in Toronto, for SPA. So if we already have these spreadsheets being filled out early in SD, why not add embodied carbon metrics to this as well? And so we intended that this would be one possible use case. EPDs and later stage emissions will be project specific. So as much as our database we think is valuable, it also needs to be adapted for each project when new EPDs become available, and also for project specific EPDs in specific locations where your project is. So please check out our new tool that Rahana showed and provide feedback. I know we're I don't know if we're talking much to a designer audience or more to policymakers, municipalities, but is this tool useful to you? If not, what is your use case and how can the tool be adapted to suit? We do plan to build off of this tool and off of this research to help make this kind of more applicable across the board for our industry. Some future work we've already considered is including common glazing assemblies. This is just something we could not get into in the scope of our study. More attention given to retrofits, as these are a critical component of the decarbonization of the built environment. We'd like to do more of a sensitivity analysis, comparing options with in each component type. We did a little bit of this on insulation cladding, but also backup structure and other elements within the enclosure design. What is the impact of additional materials at transition? So what about window perimeters and at parapets, since there's additional materiality here? And when again, in that spreadsheet, we do have takeoffs for the lengths of these, so we can potentially add some metrics to that. Optimization of whole building carbon reductions for electrified buildings. So as the thermal enclosure improves, so does embodied carbon, and we want to understand what is that balance point. Okay, that's everything. Sorry we didn't leave too much time for questions, but we're happy to answer any that come up.
Thanks very much, Kelsey and Rihanna, for your detailed and very technical presentation. Yes, not much time left for questions, but I also wanted to confirm with you, because one of the questions was, and yes, we will be sharing the recording and the slides, and we are going to share that spreadsheet and tool to you after by the end of the week probably, so you can test it and provide feedback. And with that, I just wanted to confirm, Kelsey and Rian, that you're also okay of sharing your email, so that if a feedback comes, then they can reach you. And similarly, if you have questions that are unanswered today, you can email me or email them for that. We'll do like one question, which is, does the analysis allow for changes in electricity carbon content? Meaning, does it allow us to provide an electric energy kilowatt per hour input, so that can be adjustable for those emissions based on how the grid changes?
Yeah, so two things. One, our email is at the bottom of the online database as well. So of the website, there's a link to our emails at the bottom of the website as well. For the question about, does the analysis allow for changes in electricity carbon content? So essentially what it is cut sheets with data in tables. So there's no input this, output this in this tool. There is for one-click LCA, I'm sure, modifications to that if you're actually using one-click as a tool. But for the outputs of this study, it's just tables with the analysis and data in it. So there's no specific outputs. The electrical grid is based on the sourcing of those generic EPDs, which, as Rahana mentioned, is an industry average. So we can't tell exactly what fuel source and where those are coming from.
Right. Carly, would you like to very quickly ask your question as we are at the end of the webinar? And I'll unmute you, Carly Connor, as your hand is up. Maybe it was by accident. That's okay. Last question, how to handle balcony edges and other thermal bridges?
Yeah, so that is part of that kind of future work where we have thought about transitions. Obviously, we already consider those in the overall thermal performance calculations of our buildings as like a linear thermal bridge. But we've thought about that. How do we address some of these linear elements that aren't part of the enclosure and include those in the overall calculation at an early stage?
I could touch on that as well. So while they're not included in this study, a typical whole building embodied carbon calculation would include all materials. So those thermal bridges would be included if this was a real project and we're doing a life cycle analysis of the design. The issue comes when early in design, you don't necessarily know what those transitions are going to look like. And you don't have the ability to calculate material quantities at such a concept stage. So by focusing on the enclosure assemblies that we know generally what they will look like, we're able to provide a little bit more detail within that concept stage. Yes, transitions are not necessarily included, but we're trying to focus on the big blocks. So we have a lot of understanding on operational carbon in early stages, and we don't necessarily have that for embodied carbon. So when we're looking at our enclosure assemblies as a whole, even though we don't have all of the details, it's still a significant amount more information that we can now use to make reasonable decisions and balance our carbon emissions across the board.
Yeah, and I'll just add really quickly that the reason why we focus on enclosure is obviously because our specialization is kind of around improving the enclosure, both from a building enclosure standpoint as well as a performance, like passive house, hitting net zero carbon, those kinds of things. But then we didn't touch on structural, of course, because we're not structural engineers, and also we know structure is a really big component of overall life cycle carbon. But there are a lot of people better suited than us kind of already addressing that issue. So, but there was really no one addressing this on the enclosure side.
Right. Yes, thank you very much, Kelsey and Rihanna, for this 1 hour presentation. Thanks for everyone who joined us and for your questions. And as mentioned, I will be sharing the proceedings of this webinar by the end of the week. I wish everyone a great day for the rest of the day, and stay tuned for more of our webinars. Bye. Thank you, Rihanna and Kelsey.
Thank you.
Thank you.